Okay, so just so before we keep going here, I don't actually see where it asks you to do this, but let's quickly make a histogram for what this one would look like, so we can see. So just while we were waiting for that one to upload, we took a look at this question. So here again is x, 0, 1, 2, 3, 4, 5, 6. Here's p of x, where where I've calculated the the probability of each thing. It's the same thing as what we just did, right? Just a little bit more exact. And then I went through and you'll notice that all the probabilities add up to 1. Our probabilities on our answers here may not actually add up to 1 because we did a bit of rounding. But you can see that when we don't round anything, they add up to 1 perfectly. And I went ahead and did the expected value, right? The x times p of x, and then added them all up, and they got 3.33333 exactly right. So again, you can always use this method if you want, but keep in mind the formula is a much faster, more efficient way of doing it. So if we were going to make a a quick histogram here, let's take a second to do that. Okay, so we're looking at a histogram that looks, something like this. The 0, 1, you can barely even really see down here. It's the probability is so minuscule. And then we have, 1, we have 2, we have 3, 4, 5, or 6. Again, 6 and 0, quite unlikely. 5 and 1, quite unlikely. But 2, 3, or 4 are all fairly likely. And they all sort of correspond with our idea that the expected value of this distribution is equal to 3 1/3, right? If we were to select this jury 1,000 times, the average number of women you would find on that jury is 3 1/3. Okay. Now, let's take a look at another problem. Again, a jar contains 7 yellow, 3 green, 5 purple, 6 red candies jumbled together. What's the expected number of red candies among 5 selected candies from the jar? R here, right? Remember, R represents how many candies we are selecting, which we are taking 5. A represents the number of desirable choices. In this case, we're counting red candies, so what we're going to do here is equal to 6. In our case, it's the number of red candies. N is our total number of candies, right? It's number of items in total. You can see here we have 7 plus 3 plus 5 plus 6 is 21, which is our number of candies in total. We cannot decide on a value for x, remember, because x is equal to a variety of possibilities depending on the value of big X, right? We are investigating. So, we could use this. We could find, what are the chances of getting 1 red, 2 red, 0 red, and so on. X would have to change depending on what situation we're looking at. Of course, R, A, and N, though, they don't change. They are, they remain the same. Okay. Let's try, so this one's just, it's just meant to help you practice using the formula, like what the parts mean and so on, applying them to a situation. Okay, wildlife officials tagged 350 seals from a particular colony. 40 seals were caught later, 17 of which were tagged. What is the approximate size of the seal population in this colony? Okay. This is an interesting question. It involves a couple of different ideas. And what we're going to do here is work the expected value equation, just working it a little bit backwards, right? So n would represent the total number of seals here, which we do not know. That is that's the question we're being asked, right? What's the approximate size of the seal population? We don't know. We do know that A, however, is 350, because that's how many number of seals which were tagged. And we also know that R is equal to 40, right? Because 40 seals have been, sampled, let's say, right? So if you think about this, what we're trying to ask here is, it's like, okay, they went out and tagged a bunch of seals and then released them back into the wild. Then later on, they capture a group of 40 of them and count out how many of them are tagged. This is their strategy for estimating the size of an animal population, right? Because you can't go around and count each individual one. We use this sampling technique instead. We know, right, that what we're gonna assume here is assume that EX, the expected number of seals out of our 40, is equal to the number that we found, which is 17. Now this is an assumption, but basically we're saying that assume that the 17 seals we found tagged is the expected value of the operation. Right? So it's like it's almost like we're going to use this piece of information now to work backwards to figure out what n has to be, right? So we found 17 out of 40 of them were tagged. Let's make the assumption that that 17 is the expected value, that it was not a fluke result, but that it was in fact a value that we should expect. And then we can simply solve this equation by substituting, right? A 17 will take the place of EX. R is 40, A is 350, and we divide by n, right? So 40 times 350 divided by n is going to be our equation here. So let's swap n, bring n to the other side. 17n is 40 times 350. 17n therefore is 14,000. And then n is equal to 14,000 divided by 17, which is 14,000 divided by 17, 823.53. So our estimate of the size of the population, let me just make sure I did that right here. 40 times 350 is 14,007 divided by 17. Yeah, all right. So equals approximately 824 seals in the population. And we use this expected value idea to work backwards, assuming that the sample that we took is close to the expected value. Now, of course, this may not be right, but it's an estimating technique, and it will probably be accurate, most of the time. And keep in mind, right, that counting the entire population is unrealistic, right? So we got to come up with other ways of accomplishing that. Okay, let's try another one of these distribution problems. So what do we have here? We have three more. Okay, just give us a sense of what to expect. Okay, so here we have a hat contains 20 names. So right away, again, we look for n, we look for a, r, we look for x, and we keep in mind that x is going to be a variable value. In our case, it's the probability that at least 2 female names are drawn. So let's find the probability that 0 or 1 female names are drawn, and then use the complement. That would be the more straightforward way to do this. N is 20, A is 12, right? Remember, 12 is desired individuals. In this case, we're looking at, again, female names. So A would be number of females. And R would represent the number we are choosing, which is 5. 5 names drawn. Okay, so N is 20 names. 12 of them are female. 8 of them are male then, analogously, right? 5 names are drawn. And X, what we're going to do is we're going to calculate 0 and 1, and then use the complement. Again, simply here we'll go X, keeps making it uppercase. Probability that our random variable x is actually equal to that x. We're looking for 0 or 1. And once again, I'm just going to use a GeoGebra here to help us calculate. So n was 20, right? A was 12, and r is 5. Okay, now s is 0. So let's examine our first option. Our first option is that we have 12 women, but we're choosing 0. We have 20 minus 12, or 8 men, and we're choosing all 5 to be men. This is going to be divided by 20 choose 5, because 20 choose 5 is how many different ways there are to pick 5 people, period. Of course, the probability here is very low, 0.0036. because it's not likely that you'll choose all men, right? It would be quite uncommon, quite unexpected to find that. The probability that we choose one woman, again, all we need to do here is simply change our value from 1. What does that do to our equation? It puts a 1 right here, and it changes this from a 5 to a 4, because now we're only taking 4 men instead of 5. And we see this increases the probability quite a bit, so 0.0542. And this then becomes our answer. So since the probability that x is less than or equal to, or let's just say less than 2, is equal to, what is this here, 0.0578, right, adding those two up, we can say that the probability that x is greater than or equal to 2 is 1 minus that number, 0.0578, which is equal to, what would that be now? 9422. This is the complement, right? Is using the complement. So our conclusion: probability that at least 2 female names are drawn is equal to 94.22%. Okay, so again, it's quite likely that because of the females outnumber the males, right, 12 to 8, it's not going to be that common that no females are chosen or only one is chosen, because there are more women than men in this question. If we were to look at this question again, where we're looking at the distribution this time, so let's change this to the number of women drawn from the hat. And what did I do here? I changed n to be 20. X, of course, is variable. R is 5, and A is 12, right? There's 12 women. And we see that, in the probability distribution, almost never will you get 0 women. You'll get 1 woman only 5% of the time. More likely you'll get 2, 3, or 4 women, right? If we look at 2, 3, and 4, the probability that you get 2, 3, or 4 is 89%, right? If we add in all 5 women, the probability is 94.22%, which is exactly identical to the way we did it with the complement. But of course, the way we did it, we only had to look at 2 answers, whereas if you're going to do it this way, you'd have to look at 4, right? So again, it's a time-saving thing, just like it was in the units past. Okay, this is another one, sort of marble question. It's the same kind of thing, right? 10 red, 15 blue. We can solve this one quickly so you have the answers, but I think by now I'm hoping you've got the hang of this to the point that you'd be willing, you'd be able to solve one like this. A is our desirable marbles is 10, N is our undesirable, our total is 25, and we are choosing 5 again from the bag, so R is equal to 5. Now again, we'll set S to be how many successes we want, right? How many of the 10 red marbles we're interested in. So if we want exactly 2 red marbles, we know this is going to be 10, choose 2, times the 15 blue marbles, choose 3, divided by the 25 marbles, choose 5, right? That's the formula we're going to be using again and again. And again, just using this to help us kind of calculate that. 10, so S is equal to 2. So we have 10 choose 2 and 15 choose 3, which gives us 38.54%. 0.3854 is our percent there to calculate the probability of getting exactly 2 red marbles. Again, if we're to have no more than 2 red marbles, that would be the equivalent to saying p that x is equal to 1 plus p that x is equal to 0, right? No more than 2, in fact, includes 2, so we'll have to add x equals 2. And maybe we'll just take a quick moment to mention that here, x equals 2. Okay, so we've already solved x equals 2, right? We did it up here. This was the 38.54%. So let's just simply add all of these ones up. So x equals 0, x equals 1, x equals 2. This one we've already done, so 3854 can go in for x equals 2. For x equals 1 and x equals 0, again, we'll just use the GeoGebra to solve it, but 10 choose 0, 15 choose all 5.